Okay, so we are talking about various achievable schemes for the very basic Gaussian channel. So the capacity region we said looked like this, and usually one is interested in approaching points on the dominant face. We said one point was here, one here. Then we gave an example where, you know, sometimes this pentagon is very skewed, so especially if one user has much more power than another, and often in wireless channels this happens, right? So, you know, the power, the SNR differences can be 20 dB or more. I mean, there can be extremely large differences. So I promised you some methods for achieving points on the boundary without time sharing. We talked about one way with successive cancellation with time sharing, which is already a good, nice method, right? I mean, it's not bad to go for the corner points and do successive interference cancellation. Now, what you can do also when you do this successive interference cancellation, right, we had this box where we had the decoder for message 1 at the lower rate. So we had message 1 hat, and then we did a re-encoding, and then we got x1 and w1 hat, and this we used to subtract off from this, just to go through this quickly again. And then we did a decoding for 2 to get w2 hat, and then we're done, right? Now, what we can do in this situation is also do some kind of iterative processing instead. Let me give you an example of that. It's given at the end of this chapter, but if we, for instance, suppose both users, so one way, as you see, there's kind of a loop here already. So what you can do is effectively repeat such a loop if you like, right? I mean, we could do this now. We could build an encoder too. I don't know, you know, you might think, okay, so why should we do this again? Now we could try this for decoder 1 again, right? But you see, we're just repeating this loop, E1 and so on, and then we could just keep doing this, right? One possible reason for doing this is that you might be choosing log likelihood ratios here. Now, in this case, it's sort of hidden through the encoder, but still, you could do this if these were bits. So, for example, just to draw a diagram, suppose both codes were here at low density parity check codes, and suppose we're using binary phase shift keying. In fact, even better, maybe they are, well, low density parity check codes is fine, I suppose. They could usually, low density parity check codes are built as repeat accumulate codes. But in any case, let me just draw it in this following form. Suppose we have x11, we have x12, x13, x14, and so on. And maybe this is here is 2, 3, 4, 5. Okay, and so this here might be, you know, nodes out of the low. This might represent the parity check matrix of the first code. Right, and so on. Right, so there's the values of the first code, right? I mean, it's just the parity check matrix, and these nodes represent the values here. Well, if the second user also uses a code, well, we have the same thing, right? So we have this structure, so we'll also have 5 symbols, x121 to x25, and you have the same kind of picture. Maybe this code here has a higher rate, so it has fewer parity checks. And so on, right? So this is parity check matrix 2. And now if we draw what's happening, the factor graph of what the channel does, all the channel is doing is adding these two together. And so we get the channel output nodes, of which there will be 5, because there's 5 channel outputs. right? And now the log likelihood ratios you get will enter here, right, from the channel. So you just take the channel values, you scale them according to the signal-to-noise ratio. That's how you build log likelihood ratios. And then we just start message passing, right? Go through here, come back and forth we go, right? That's soft interference cancellation. Or if you think about it, it's just one big factor graph. Now when you try this, you'll notice that the decoder won't converge. And the main reason is it doesn't have a good place to start. So what do we do to make it start? Well, there's a very simple trick, and we'll talk about that, something like this in a moment. Suppose just in the first channel use, user 1 doesn't send anything, and maybe do this. Well, now this guy gets started. Now, of course, it won't just be 1. We'll leave out like maybe, 1% of the bits for very long code. Then this guy here will get started because there's no interference, and then you'll see a wave propagating through. It's kind of like spatial coupled decoding, because it is a spatial coupled process. If we leave a certain percentage of nodes here open, the whole thing has a place to start. You go back and forth. Okay? That's how you could achieve any point close to this boundary, also in the middle, without time sharing. That's one way to do it. Okay, and it's interesting to do. So there were some first studies on this. I think the group from EPFL, so Rudiger Banka's group, Abdulaziz Amraoui, during his PhD, worked on things like that also for the broadcast channel. And they discovered, okay, they had a hard time getting going, although at that time I don't think they had the spatial coupled trick yet. So they tried, I think, other tricks to do it. It's a little bit like something called code doping. So there's a terminology called doping in codes, where doping means you throw in some known bits or some low, you dope the code with a little bit to make sure it gets started in decoding. That's what code doping is. It's a terminology from Stefan for using these exit charts just to raise the exit chart up a little bit, and then you get started opening a tunnel to decode. And so this idea of like doing a spatial coupled like structure was also, one person did a lot of work on that, was a young assistant professor in Halifax. Fortunately, I forget his name now, but he visited us several years ago already. So he looked at that in some detail, especially if you had more than one users. You can imagine just shifting the users, and then you can get all the decoders started and get that stuff propagating. So that's one way to do it. So that's a little bit of a, iterative decoding perspective. The second one is something called rate splitting. So let's talk about that. Well, we've already seen what rate splitting is. Rate splitting involves taking one of the messages and splitting it into two pieces. So suppose we do that with this message here. Suppose we do the following. Suppose we convert this 2-user multiple access channel into a 3-user multiple access channel, where what we do is we'll split these rates into 2. So suppose we take W2 and split it into W21 and W22, and suppose this one has rate 1 and this has rate 22. Okay, and then what we'll do is we'll do successive decoding like we talked about here, just with a slight variation that we now are decoding 3 codes. Okay, so what we'll do is we'll choose one rate here, and we'll first decode, so we'll do it a little bit differently here. So we'll first try to decode this code with interference. So what will we get if we do that? If we decode, so this thing here becomes the following, right? So x2, so then now we'll choose x2 here of W2 to be x21 n times W21. So we'll use superposition coding times, let's say some, well, we can choose the power level later, plus x22n W22. Okay, and so we'll choose these code books to have, they have lower rate, and then we add them together. So we just have to make sure that the power we use here, let's call it power to 1, And the power we use here, power 2 sums to the power of user 1, right? And now what we'll do is we'll decode using successive interference cancellation again, but we'll first decode this one, then we will decode message 1, and then we'll decode the final one. Okay, and so what kind of rates do we get here? Well, if we decode this one first, I will get x21y without any interference cancellation. So if you like, you know, here you can just redraw this. This will be w21, x21, but it's the same picture, right? Just with 3 steps. Then we subtract that off. Here we'll have decoder 21, here we'll have decoder 1, and here we'll have decoder 22. And so here we get w hat 1, this is going to be encoder 1, this is going to be encoder 21. Subtract off, and then we're done. Right. W22. And we can quickly compute the rates. We'll get ix2y plus ix1y given x21 plus ix2y given x1, 22y, x21y, x1, right? So we'll get that triple that we will get. And now if I compute, if I use that to compute the powers, what I'll get here is 1/2 log. So here I'll get 1 plus the signal to interference plus noise ratios is P21 over maybe, well, I'm thinking about making alpha. Let me make this here right away, alpha P2, and make this alpha bar P2, where alpha bar is 1 minus alpha. Then that way I can have one parameter only, alpha P2. And what's the interference plus noise ratio? Well, it's going to be P1 plus alpha bar P2 plus 1 if the noise variance is 1, or plus n if we're saying, I guess we're using n. Right? Signal to interference plus noise ratio. Here we'll get 1/2 log, again a signal to interference plus noise ratio, but now with less interference, plus P1 over alpha bar P2 plus n. And here we'll just get a noise because we're canceling out the alpha bar P2 over n. Right? And now let's see what rates we achieve here. First of all, when we take the sum, you'll see we get the full thing. That's the first thing we need to check. We want to show that that sum gives us, by summing those all up, we're just getting the sum rate. So let's see, when we add that all, the best way to do this is just always bring this to the top and leave that at the bottom. It's actually quite easy to see. Just take this to the top, right? So 1 plus this we'll get P1 plus alpha bar plus alpha P2, which is P2 plus n. So what's on the top is what we want, and then at the bottom we get this. But now look at what happens here. What's on the top here is what's on the bottom here. So they cancel when we add. And then we have this in the bottom, and what's at the top here, we'll cancel that, and we just have n left. And immediately we're definitely on the dominant face. And now let's see what happens as we vary alpha, right? As we vary alpha, suppose we start with alpha equals 0. This goes away. Here we'll get 1 plus P1 over n. And here we'll get, hold on. No, a P1 over P2 plus n, so that then we're here, right? This is alpha equals 0, right? If alpha is equal to 1, then this is 0, and we get P1 over n, and here we'll get P2 over P1 plus n. So then we're operating here. And if you go alpha in between, you can walk down that line because it has to be there, right? Because the sum is full. So alpha equals 1/2 if it was symmetric would get me right to the middle. So this is one way of achieving without time sharing, so we're not wasting time through time sharing, of getting points on the boundary. So practically it's interesting. On the other hand, there is some disadvantage, right? We do have to create 3 code books, right? So we have to make sure they're all good. We're now doing successive interference cancellation with 3 levels. Again, you know, the implementation's a little bit tricky and so on. Still, this got a lot of interest, this idea, in the mid-90s. So Bixio Rimaldi and Alex Grant, and I think this was part of Alex Grant's PhD thesis, perhaps even, this sort of rate splitting approach. It's a nice approach. Okay, so that's the second way of getting it. So we now have had this just soft message passing, which is also kind of nice. Here we pay a price in a different way. One is through iterations. Here we're doing 3 levels of concatenation. Now I'd like to present a third approach, which is I've rarely seen in books, but it's the nicest of all of them, I think, but because it was only really presented about 10 years ago. And it's very similar to what I described. What we're going to do is we're going to shift transmissions. So let's look at that and see what happens. Okay, first, any questions about this rate splitting? Of course, this generalizes. I mean, if we have now 3 transmitters, we'll split pair. You know, everyone will split except for the first, and you can just do the right order. So it takes a little bit of work to figure out everything, but okay, it works. Okay, so let's try another method, which I really like because it's so simple, and I know Young Han Kim likes this too. Suppose we transmit in blocks, which you always do anyway. And suppose here we're transmitting x1, let's say block 1 n of w1 in block 1. And now we'll have another block, x1 block 2 n, w1 2, and so on. And now, so up to now, the pictures, everything is frame synchronized, right? That we have here the block. But suppose we don't do that. Suppose we shift this guy a little bit. x21, block x2 at block 1, w21, x22, and block w22, and so on. I mean, I didn't really draw it proportionally. And suppose this shifting here is a fraction of alpha n, which means, of course, that this fraction here is alpha bar n, right? It's just n. The whole thing is n symbols. This is n, right? Okay, so now what we do is we'll compute. Suppose we just first decode this one here, xw11, by itself. You'll notice there's no interference in a fraction of time, and there is interference in the other fraction of time. Okay, so we have to compute what the information rate is over this block, and it'll just be the average of this information and this. But the information here is going to be alpha times the mutual information without any interference, which is the same thing as writing I x1 y2 given x2 equals 0, right? For the Gaussian channel, it would be 0, but let me just write it more generally as x2, right? Because it's the same as having no interference. Plus alpha bar with interference, right? Which is going to be I of x1, y2. Okay, now you already see all we're doing is we're shifting between this point here and this point here, and we can choose by how much, right? And now, after decoding this guy, we'll decode this guy. But look, he has 1 minus alpha of interference, so it's just going to be alpha bar of I x2 y. Sorry, should have been a y. x1 plus alpha I x2 y, right? Because the fraction where you're getting interference is this. And now if you add these two up, you get R1 plus R2. This is alpha plus alpha gives me alpha I x1, x2, y. And this one here is alpha bar plus alpha bar, which is just 1, right? So we're on the dominant face. And the alpha, again, lets us shift in between. If alpha is equal to 0, we're up here, and if alpha is 1, we go down here. I mean, this is a much prettier method, right? Nothing special, no extra codes, no rate splitting, no special iterative processing across both receivers. All we're doing is time shifting. That's it. And decoding separately with treating interference as noise. Okay, really straightforward. So, and I think practically, and this is, the first time I saw a paper that actually does this was around 2006, and it was Henry Pfister, a student named Ho, but they were this, Qualcomm group. Henry's now at Duke University, but he first went through Texas. But anyway, a very nice idea, right? And actually, this idea you can apply generally whenever you have multiple users transmitting in a system. It's really just a matter of placing their timing in a certain way in order to move things around, rates around. So it's rate adaptation by timing adjustment. Very, very simple. Okay, so I think that's a very nice approach. So that's the third method. I like to call it offset encoding. But okay, I think they have there's other names for it too, but it's a nice trick. Okay, any questions about that? So that's something worth remembering, I think. Okay, so now the next thing I want to do is talk a little bit about the vector multiple access channel. Just like we talked about the vector broadcast channel, talk a little bit vector channel. So now our model is going to get slightly more complicated. Y is equal to H1, X1. So this is a matrix plus H2, X2 plus Z. And in general, this Z has covariance matrix, zero mean, and some covariance matrix, QZ. But the nice thing, again, so this is already looks a lot more complicated. This will generally have, let's say, n, let me call it n tilde receive antennas, because we're using n for noise variance. Well, I guess right here we're not, so, well, maybe let's do n. So this will be M1 transmit antennas, M2 transmit antennas, right? So sometimes you might be able to, one way of calling this would be the M1 by M2 by N, MIMO MAC. Okay. So, and in particular, a common case that's studied is when M1 is 1, so this is just a scalar, this is a vector then, and this is a scalar and vector. So for example, for two users, you might want to consider using two antennas at the receiver, because that, in terms of capacity scaling, that's the best you'll be able to kind of, multiplexing gain, you'll be able to get as 2 here anyway. Fine, so things get more complicated, but fortunately all the information theory is, all already there. So everything we just did here we can redo, right? So the only thing that we have to do now is compute mutual informations with these vectors, x2. So that's the power of the information theory. We are treating very general problems and can just, even though the problem changes its shape, the basic equations are all there and remain the same. So all the insight we've gained from the scalar case we can apply now to the vector case, right? And hopefully we'll gain insight. So let's just talk about the capacity region. So we need to look at this. Now formally I have to have this U again, but for the same reasons as before, the U will not play a role. We can quickly use it anyway though. So this thing here is the summation of U of P of U, I of X1 given x2u. And the reason we don't need to worry about the time sharing is because we'll see that Gaussian, that there's a certain concavity property we get. Now, here we can write this again as h of y given x2 u equals u minus h of y bar given x1, x2, but then we just get noise. So we'll just get 1/2 log 2 pi e raised to the power of the length of this vector, which will be n of the covariance matrix of the determinant of the covariance matrix, right? That's the entropy of the noise, of Gaussian noise. So you always have, here we have to raise to the length, and here we get the covariance matrix. Fine, and this one here, well, we can write this here as, again, we can since we know x2, we can subtract that piece off, so this just becomes h1 x1 plus z. But of course, you know, all these guys, I guess I have to have u equals u, right? And this thing here, again, we can compute its covariance. Oh, I forgot the constraint, the power constraint. So the power constraint is just the usual one, right? So the power constraint is now a well, power constraint is the following. So 1 over m summation from I equals 1 to n with or without expectation, but let's just do it with the expectation of x1 squared less than or equal to p1, and same for user 2. So that's I, the ith vector, right? Just less than pk. So what that means is we have a covariance matrix constraint on this, right? And so under a certain covariance matrix constraint, we know that a Gaussian distribution maximizes entropy. Same idea here. So this whole thing is less than 1/2 log of 2 pi e to the n. The covariance matrix of this, which is going to be the determinant of h1qx1 h transpose plus qz. Okay, so putting this all together, given u, so this qz should be a function of u, right? So it's a function of u. So this, maybe I should put that in here. So we're here, since we're time sharing, we're putting qu. But now it turns out that this log of determinant quantity is concave in what's inside. And so we can bring the pu inside and say that that logarithm is less than, that averaged logarithm is less than the logarithm of the average of what's inside. So there's a concavity property here. And because of that, we can say this is less than or equal to 1/2 log of the first term h1 q x1 h1t, where this is averaged, plus qz divided by qz. So it's just the signal to noise ratio in this sense. Okay? And we get equality if we choose this to be Gaussian. And since if the average power constraint is, if the power constraint is met for the average, then the average meets the power constraint, right? So that's important to check that we don't have a change in power. But anyway, there it is, right? So that's the first one. So the rates will get look like this, R1. Just to repeat this, we could even choose the covariance matrix to be the identity matrix. That's what's usually chosen. Then the determinant of the bottom is just 1. So maybe we simplify a little bit this through that. Usually it's not hard to deal with. Usually what you do here now is, if you don't have covariance matrix 1, we can create a square root of a positive definite matrix and then multiply both sides by the inverse square root, and then this becomes I, and we just get an effective channel with QZ to the minus a half times H1 is the new channel. You know, so then effectively we get something that has like almost like an identity matrix. Anyway, let's just simplify and choose QZ equals I. The main point is both cases are basically the same. So we get log now of the determinant of H1 QX1 H1 transpose plus I, let's say. And similarly with R2, of course, by symmetry, we'll just get the same thing. H2 QX2 H2 transpose plus I. And for the sum rate, we'll also get something similar. We'll get log of what you would expect, H1 QX1 H1 transpose plus H2 QX2, because they're independent, H2 transpose plus I determinant. Right? So those are our rates, right? Okay, so like I mentioned, a common situation is where the transmit values are scalars, and this here is a vector. In this case, so we can take a look at that case just especially for the moment. So suppose n1 equals m1 equals m2 equals 1, and let's suppose n equals 2. So this is like the 1 by 1 by 2 MIMO max. There are various situations that can occur here. Let's just quickly compute what this is then. So then the R1 becomes 1/2 log of the determinant of a, this will be, I'm going to view it as a column vector. So let me write this as a column vector times QX1 is now easy. It's a 1 by 1 matrix, right? So it's just power 1. Here we'll get H1 transpose times P1 plus 1, right? Now it's plus 1. Plus I, apologies, plus I. It's a 2 by 2 matrix because there's 2 receive antennas. But you know that if you have a vector times this, this determinant is the same as just flipping things around, right? So turns out this is identical. This thing here is the same as P1 H1 squared. P1 H1 squared as a vector plus 1, right? It's the same thing. Okay, and the same thing will happen here for, so it gets easier to calculate. However, this term won't get so simple. So if we look at the sum rate bound, yeah, so let me just change these to the scalar case. Okay, so this thing here is what we just did. I think it's going to be a little bit easier to think about. So this is going to be P1 H1 squared as a vector plus 1. Same thing happens here. This one will be P2 H2 squared. And of course, this should not surprise you in some sense, right? Because the maximum, the capacity of the channel I have to be careful how I put this. No, I don't have to be careful how I put it. Suppose I just have one transmitter, right? What are the rates you're going to get? Well, you're just going to use maximal ratio combining if you have 2 antennas, right? And what does maximal ratio combining give you? You just get the power of the channel as your SNR times the power, right? So that's exactly what you're getting. And same thing here. So this is just a maximal ratio combining for the second user. But of course, the maximal ratio combining for these two might be different, and that's where the problem will come for this bound. Here it's true, we will get H1. Here we will get H1 as a column vector times H1 transpose P1 plus H2 as a column vector H2 transpose P2 plus I, but now we can't necessarily do this trick of making, because the trouble is the directions of these two vectors might be different depending on like where they are spatially. So let's do some examples with that. So one example is, for instance, suppose they're perfectly aligned. Suppose H2 is just beta H1. So suppose these were collinear. If they're collinear, well then we can just write here beta H1 H2 transpose. So then what's in here becomes H1 H1 transpose P1 plus beta P2 plus I, and the determinant of this is again the same form as before. We have one vector which is one dimensional, and this here is the same as H1 squared P1 plus beta P2 plus 1, right? So what's happening is we can use the same maximal ratio combining to decode both users, but since it's the same maximal ratio combining, the channel has effectively become a one antenna receiver now, right? Because both channels are pointing in the same direction, right? Geometrically, this might correspond to a base station, right? And one user is here and another user is right behind him in a way, right? So maybe here and here, right? So the direction of the vectors is exactly the same. So, and that's not good in terms of getting good rates, because the trouble is here now we're not being able to use any spatial multiplexing at all, right? So we're not getting any spatial directions. Changes. So let's do another example, which is more interesting from spatial multiplexing perspective. Namely, suppose these two are orthogonal, right? So suppose H1 transpose H2 is 0, right? Now these channels are orthogonal, so it's effectively, you might have one person here and one person here, right? Something like that. So if they're orthogonal, what's going to happen? Well, now we can completely, separate the users at the receiver. And what I'm going to do is something very simple. I'm just going to use a post-processing of Y using this orthogonal matrix with H1 in one row and H2 in another. So what we do is we use an equalizer at the receiver, or it's just a linear equalization. So what we'll do is we'll convert Y to Y tilde by using H1 transpose and H2 transpose times Y, right? So this is a length 2 vector. So this is a 2 by 2 matrix, right? 2 by 2 matrix with H1 transpose in this column, row, and H2 transpose in this row. And since it's invertible, right, if we assume that none of them has 0 power, then this matrix is invertible. So the mutual information between x1, x2, and y is the same as the mutual information between x1, x2, and y tilde, because I can always invert it, right? So I don't lose any information there. So now I can look at the covariance matrix of this. So if I just plug that in, so I'm going to plug in y now, right? So this here is just going to be H1 transpose H2 transpose times H1 x1 plus H2 x2 plus z. And you see what we're going to get is, here we'll get H1 squared, we'll get two pieces, H1 squared x1 plus H1z transpose, and here I'll get H2 x2 squared plus H2t z. Okay, so we've effectively now, and moreover these two here are orthogonal, H1t and H2t, so these two noise numbers are independent, uncorrelated, and hence independent. So we have two parallel channels, both with the full beamforming, right? So that's nice. So what is the rate? It's just going to be the sum of the rates of the two without any interference. So that's a very different situation, of course. Now the rates we've achieved here for the second case are simple. They're just going to be the sum of these two rates, right? That's all it is. Okay, because what's going to happen, I'm going to get h1 to the fourth, h1 squared, and then the two will cancel and so on. Anyway, this thing here, if we look at the region, all that's happened in this case, interestingly enough, is the rates bounds look exactly like this. They exactly touch, right? So all bounds are active, including this one, but this one happens to be active only in one point. So we've totally separated the users. Now, of course, in most cases we have, for two 1 by 1 by 2 channels, well, they're not perfectly separated and they're not perfectly aligned. They're somewhere in between, right? So what do we do now? Okay. So one way is just to invert the channel. So what we do is we again stack a channel. We can consider the channel H. So we can write this, by the way, like this, right? So I can write this channel by doing this, H1, H2, X1, X2, by just stacking vectors, right? So I can always do that too. So that perspective is useful because now you can see we can do an equalization on this channel by, it's like an intersymbol interference kind of channel. We can multiply on the left by any matrix we want, and particularly we can invert this channel. So the simplest approach is just to use the inverse filter. And that'll work well as long as this matrix here has, of course, full rank, but also is well conditioned. So if this here becomes a fading channel, sometimes you might get a really lousy channel, but as long as most of the time it's good, that gives you actually pretty good rates, and that's the most common way of doing multi-antenna communications. And generally it works quite well. But there might be some cases where that doesn't work well, of course. We could also use an MMSE filter, and so on, if you're using linear equalization. So that's what we actually did here. We just used the inverse filter, modified by something. But anyway, we effectively used the channel inversion by choosing this approach. Okay, so what do we do now in the general case? What's the best thing to do? Well, now we won't have a situation. So we could think about linear equalization, but suppose we use nonlinear equalization. Which method do we know and love? Successive interference cancellation, right? And that we know is even the best possible. We get corner points, right? So why not just use that? And so that's one approach we can do to get the best performance for the general H1 and H2 spatial directions approach, right? It's again the same idea. So let's talk about that briefly. It's actually quite straightforward because all we have to do is measure these, just have to write down what are the rates. Well, the rates are, again, quite straightforward to calculate. So anyway, in particular in this case, let's just write out what it is. I don't know if that's even worth it very much to do. I mean, this point here is just given by, this big sum rate thing, right? So let me just I of x1, x2, y, here I'm assuming scalar, minus this, term here, right? 1/2 log p2. Anyway, it's just going to be rate 1 is going minus I x2, x2, y. Well, of course, it's just this number here. It's ix1y. It's ix1y. But I can calculate it from those expressions by just subtracting out the ix2y given x1. Right? Comma I x2y given x1. But effectively, I would just be treating interference as noise. So what I'm going to do at the receiver is first decode this one here by treating the interference due to the x2. There's no beamforming because it's just a scalar as noise. Subtract it off, and then I operate at that corner point. And then I can do time sharing to operate in between. Right, so that's one way to do it. Or alternatively, you can do that shifting in time that we just talked about. Then you can operate anywhere inside here. However, now comes the interesting. Okay, so now I have to go take one step back and go back to the general case, m1 times m2 times n, where things get a little bit more complicated because now we really have vectors here everywhere, right? And the problem is we now also have covariance matrices to optimize over, right? So if I write back what the rate region looked like, let me write that again. So we'll get H1 is now a matrix. This is a covariance matrix which we don't have only one parameter for, but many parameters to optimize, right? Because we want to do some beam steering now at the transmitter. So if your laptop had more than one antenna, it could start steering the beam too. Log det I. So all I have to do is just change it back to what we had before. And so there's an extra optimization problem here, namely in the beam steering at the transmitter. In the problem we just looked at, there was nothing to optimize. You should just transmit at your full power. But here now we get an optimization problem. Again, however, well, let me finish this here first. H2t plus I, right? Okay, and what's going to happen now is the following, and this is what's going to get interesting, is that, let me redraw this here. What we're going to do now is we now actually have to do an optimization. So with m1 greater than 1 or m2 greater than 1, we must optimize qx1 and qx2, right? Okay, and now what that means is that we'll get a different pentagon region for every qx1 and qx2. So, but suppose we do the following. The idea, what we're going to use now is the following. What we'll do is so for every choice of qx1 and qx2, we will get a new pentagon. But what we'll do now is we'll track how this point here behaves when we do the successive interference cancellation in a certain order, right? So we'll always first decode this guy and then decode this guy, okay? And it turns out if we track how that point behaves, in general you'll get a behavior across all the qx1 and qx2 that has the following form. Usually we'll get a straight piece like this somewhere. Then we'll be at some corner point. Maybe we'll do it here. And then you'll get a curve that goes down. Okay, so as you optimize over the Qs, if you decode in that order. And if we look at the other corner point, we also start somewhere, right? And as we optimize this, by doing the other successive decoding order, you're going to get the similar kind of thing. Okay? And then it'll turn out that what's going to happen, and this will generally move out, actually, in terms of sum rate. And this will also generally move out in terms of sum rate. And what you'll find is that the optimal region requires time sharing. So we actually have to sometimes operate with this pair of qx1, qx2, right, to get to this point, corner point. And then we'll have to sometimes operate with a second qx1, qx2 pair to get to the second point, and you actually, it's right here, maximum sum rate, and then we have to time share. So we don't have any way around it if we want to actually achieve sort of a symmetric style of rate. That's the plane where you want to operate, and unfortunately it requires time sharing. to operate there, because there is no pair of covariance matrices that actually operates there. It doesn't exist. So we do have to do some kind of, unfortunately, we do have to resort to some time sharing to get the maximum rate. Or alternatively, of course, we could just operate, at some point all the time or something like that. It's still the maximum sum rate, but it may not be the fair rate that we're looking for. Okay, so this is an interesting insight. When you're doing optimization for MIMO max, the behavior kind of changes. We can show Gaussian as optimal, and that the region has this form, but when you do the optimization over these matrices, you get answers like this. And the optimization over these matrices usually has to be done numerically, right? I mean, even for a point-to-point channel, that's true, right? Just think about the following case. Suppose we only have one user, and suppose the number of transmit antennas is the same as the number of receive antennas, and suppose the channel is diagonal. Well, that's exactly OFDM, right? And you know that for OFDM that you have a power control problem that you solve through water filling, right? So this is just the more, if you go more general, well, you have singular value decomposition with water filling on the singular values. Now, if we have both users, it gets even messier, right? So you can't imagine it gets any easier. So you will, finding these optimal covariance matrices for certain points here does involve numerical optimization, and usually what you do is you try to go get the furthest point in some direction with a certain decoding order, try to go the furthest, and there are numerical routines that work. You can show they converge. It's actually a convex programming problem, and you can find what they are. But okay, so there are papers on this. Nihar Jindal did quite a bit on this. But there are other papers too that simplified his procedure. I think his paper's from 05, 06, something like that. And then later there were further papers on this. Okay, any questions on this? So the MIMO case is quite a lot more interesting computationally. But if you get confused, the easiest way to get unconfused, in my opinion, is you go back to the information theoretic quantities, because they're very clean, I think. Where you get confused is with all the matrices and all the stuff that happens, but this is always, the picture fundamentally is always the same, and that's, again, the power of the theory. It really unifies everything and makes it possible to understand these complicated scenarios in the first place. Okay, now there was one topic that was listed on the list as this duality of max and broadcast channel, so I do want to do that yet, or I'll do one version of duality explicitly, and the other one I'll just describe to you.